So what the idea here is that we train a transformer to do the predictions for us. So like the traditional way of doing machine learning that you all know, with neural networks that you all know, I hope, by now, is to optimize the loss on your training set such that the neural networks models the input and the output based on the input, and it like has like a minimal loss or as small as possible. And what we do here now is we go to the meta level, and tomorrow we will have more meta learning as well. But I guess I do the first bit on this or the first intro of this. And the idea here is we train a neural network, and that neural network doesn't take in one example, so it doesn't just take in the X or like the columns or one row, but it takes in the whole table or like the whole data set. And it will condition on that whole data set and then take in an additional X and do the predictions for that additional X in the supervised learning case. And this is again joint work with Noah and with Frank. And actually Kata. Sorry, she's not here. Kata Eggensberger is missing. Okay. I'm sorry. That's embarrassing. Okay. I explained it before as well. I will do it again with a few pictures. So what we did so far, the standard procedure is we have this, I call it a small model, but I guess it's like a regular model, you could also call it, in which we optimize such that it behaves like the function that maps from X to Y, such that like the given, I don't know, a line of the table, but just not the label, it will predict the label for that line. And when we then do inference, we feed in one X, and the model returns its prediction. And then we typically even have, like here at least, when we do AutoML, we have like an HBO loop around this, and try to then optimize the hyperparameters of that loop with another loop around this. And we try to do something radically different that can still then, of course, be tuned with HBO. We actually have seen this many times that all of the AutoML tricks work as well here. But what we try to do is like we have the bigger neural network and you feed in your test example, but also your whole training set into that one neural network, and you get out your prediction. And that is the TabPFN. You can still interrupt. Okay, the idea is that we want a foundation model for tabular data, and I think actually that parallel was opened before as well in the LLM talk. So one way to think about the TabPFN is actually as like a similar thing to an LLM, where we condition on the context. So for the LLM, that's like the sentences before, and then try to predict something. For an LLM, that's the next word. And for us, the context is the training set, and what we try to predict is the label for a or multiple test examples. And our conditioning, of course, is a bit different. We condition on the set, they condition on the sequence. There are like details that are different, but generally it's kind of similar, and the architecture is even kind of similar. It's both a transformer. Everyone uses transformer, so it's, I guess, clear that it's similar. And what we can see is that even our initial version, which we released last year, could outperform many methods, but only on numerical data sets and only on small data sets. So in a very restricted setting. Like if we go out of the setting, like we're destroyed by AutoML, let's be honest. But in this setting, we can see that these LLMs, or no, sorry, these TabPFNs that are just conditioned on the training set can outperform many other methods. And actually here in this table, you see like how much time they take. And because it's just a forward pass, so it's like an LLM inference. So what happens when you call ChatGPT? They're very fast to do, while these other methods, of course, take some time to tune and stuff like Yeah, okay, this is just a sneak peek. We're working on a second version, that's why I'm still excited about this. I actually heard in the break, someone told me like, why are you actually working on this? Like, AutoML is so much better. Yeah, you're right. I just believe a little bit in the momentum, and we're very much improving here. We can see like a comparison. The orange one is our released model, and the blue thing is our new model, and we have the data set sorted by how good we are. And we can see like when we're below 0, we're worse than LightUVM default, and when we're above 0, we're better than it. And we can see that we can like make this like little thing where we're actually worse than like a very simple standard model, smaller and smaller. So we can't, like, I think we can be competitive with the trees. All right. So how does it work? Like, let's get away from the results for a minute. How does this work? And that's actually what you will do in the tutorial as well. The tutorial will be really cool, I think. Sorry, the hands-on part will be really cool. You will train your own PFNs. And now we will talk a little bit about what a PFN is. And that is, I hope we chose a descriptive name, prior data fitted network. And the idea here is that we define a prior. And what way do we define a prior? We define a prior as a distribution over mappings from X to Y. So a distribution over curves, you could say, in the 2D case, so where we only have one feature. And this is, for example, a sample from a GP prior. So what we can see here is these smooth curves that you typically see from a GP prior. And we can sample as many as we want from this. And what we want to do then is we want to get the posterior out of this. So that's the prior, and in Bayesian terms, there is a posterior. And the posterior is if we condition on a few points where we know like that's the XY connection. So let's say for these black dots, we know, go ahead. For these black dots, we know where X and Y come together, so we know like the function values. And now we want to get like what are the likely points for our curve to be between these points. I guess like a general prediction problem, just in Bayesian terms. And what we're really interested in here is like not the distribution over these mappings, because that's very abstract, but a distribution over the output. So like given the data set and given my input, so given all these black dots and given that I want to evaluate at this position, what's my distribution for Y over this dimension? That's what interests us here. And maybe like from this form, you also see the connection to what I said before. We condition on the data set, we condition on the test input, and we get out the test output. So if this is not super clear yet, I think it's kind of fine because I will explain it another time in another way. If it's clear, go on TikTok or something. So what we have here on the left are these samples from our prior. Now they're discretized, so that's actually what we will feed in. These smooth curves are just like a lot of points sampled, but in actuality, we will have them discretized. And you can think of these as little data sets here, actually. So these are just little data sets that only have one X dimension. So if they were a table, it was a table with 2 columns only, X and Y. We will treat more X's, it's just for these examples a little easier. I think I should stand here, right? It's a bit easier if we just do one dimension, right? And what we have here is that the blue dots, I hope you can see that even from the back, there are blue dots and there's a yellow dot. And the blue dots, we say they are training dots. So that's what we condition on. That's our training set. And the yellow dot is our test set. And we generate millions of these data sets because we have a different, like we have this prior, so we can just generate them. Like we generate them artificially. And these are again from a GP prior. So yeah, that's a particular prior. But you can think of like what we will look at later, rich regression prior, which is, for example, be like lines with some noise added to them. Like that's the whole thing. Like we have a line and then add some noise. And typically the priors are some like simple procedure to generate data sets that might happen in the real world, or they might also not. But they like represent good connections, like or like logical connections, let's say, between the X and the Y. And now what we do is we train a neural network to take all of the blue dots as context, and then try it on and the position of the orange dot, and then predict the height of the orange dot. So predict the Y of the orange dot. And what we do, what we get out of this is we get out something that actually approximates that equation that we had here before, the PPD. So this posterior predictive distribution. Let's be honest, only in the limit that we optimize it like completely to like the minimum loss, which we don't, but at least in this like theoretical world, this would exactly match the posterior predictive distribution. What does this mean in like real life, let's say? We can feed in something like this. This might be, I don't know, maybe here at the beginning of the Alps, like close to Munich, and you want to predict what's the height at this position. Maybe, I don't know, you're a shepherd or something, and it's very important to you what your sheep do at this position. What you would get out is a distribution over what the height could be at that longitude, let's say, at that longitude, and that I don't know, the important bit here is that this is a distribution. Typically, if you have a regression model, you get out a single value. Here, you always get out a distribution. It's because there's uncertainty in here, right? There could be many curves that fit through this, right? And we'll try to represent them all. And you get like a cut through all of these. And the third time. So this is the third time explaining this, but I hope I don't bore you. And after this, maybe ask me a question if it's still not clear. And that's like totally fine. We generate a lot of data sets, random data sets, millions typically. In your example, like if we do these notebooks, you will do, I think, 10,000 I have as a default, but you can of course go above that. And then we do a simple, actually, cross-entropy loss, so like your standard deep learning loss that everyone uses. And we just try to optimize predicting Y test given X test and our data set, our D-train. And what we will get out is something that approximates this perfect Bayesian prediction. Are there questions at this point? I guess a lot of you are not Bayesians, so that's okay. Sorry to nerd you. I'm a big fan of Bayesian stuff. Is it very clear? That's why you don't ask anything, or it's clear. Okay. Yeah, great.
Just maybe a more in-depth question. So what you typically have is not such Dirac distributions in practice where you have full probability on the actual class, but actually you have uncertainty. So do you also consider that, or is your ground truth probability distribution always a Dirac distribution?
That's a very, very cool question, I think, and we will look into this in the tutorial. You can think of our ground truth always as a sample from a distribution. So yeah, in the ground truth, we have data sets. So it's like really like X and Y, it's like numbers. It's Dirac in some sense. Yeah. But what you will get out is non-Dirac. Like you will get out smooth distributions.
I mean, you can demonstrate in deep learning tasks that if you imprecise your data deliberately, you can get better generalization performance. Because you do not force deep learners then to predict 100% accurate or 100% probability for that one class.
So you mean something like label smoothing?
It's a remedy for memorization effects.
You mean something like label smoothing?
Yes, in that direction.
So we actually tried that, and it deteriorates performance. Like it made it worse. I shouldn't use these complicated words. I can't speak them. I can say them. It made performance worse. So for us, I think it didn't help. And when we write it down, I think we're in the lucky case that everything is anyway so random that it's kind of implicitly regularized because like, there's so much random things going on. And maybe regarding the remembering part, I think what's also important to know is with these PFNs, since all of the data is generated randomly, you typically can't really overfit them. I mean, I think in like a meta level you could overfit them, but when we look at trainings, they will just get better. Like we never had it that like our test performance gets worse at some point. We can like overfit it as much as we want because we can't memorize because everything is new all the time.
It's still then quite interesting that TabPFN is so well calibrated. At least that's interesting to me.
Yeah, I would hope that it is well calibrated. I think it's not actually. Yeah, I have a different intuition there. For me, it's like worse calibrated than I thought it would. But yeah, I think that's another topic. Sorry, there were more questions here, right?
Yes, answered it.
Oh, okay.
Maybe a question.
Yeah.
This is all called the classification, right?
Yeah, I only talk about classification for TabPFN. We work on a version for regression, but it's not out yet. But we will actually later in the tutorial we will do regression because it's nicer to look at it. Yeah.
What do you think how it will, would this work for multi-label?
So with multi-label, you mean multi-class or you mean?
Multi-class, yes.
Yeah, this is all multi-class classification. So we go up to 10 classes, but I think we're not really limited in the number.
Maybe that's why with the smoothing, that the performance will look worse, right? Would it be?
Yeah, maybe. I actually don't know, yeah.
Maybe as a follow-up.
Yeah.
Multi-label?
So multi-label in the sense of
Like
you're not predicting one Y, Y1, Y2, Y3.
Yeah.
No, but how I think about it, you can always feed the other Ys as features, and then you just do multi-label that way. You just call it.
Or you start to predict one, then put it in, and then the next.
Exactly.
Yeah.
But we never tried that either, to be honest. I just thought like, yeah, we don't really need to do it that way. Yeah.
So maybe also a little bit technical question, but how do you make sure that you really, so you said that you condition on sets instead of sequences, right? Right?
Yeah.
And I think that's really important, right? Because as first of all, my question is how do you do that exactly? And second, I think it's really important, right? Because otherwise you might really, I don't know, depend on the sequence of the training that is exactly what you don't want to do.
Absolutely, 100% agree. I really hope I didn't hide that slide. It's the next slide. Thank you. Thanks for that. So how do we do that? So what we have, like what our architecture looks like is we have a transformer encoder. So for like we have the image of the transformer before. Maybe you remember there were these two parts. We only use one part to keep it a bit simpler. But I think my explanation right now kind of hinges on you knowing transformers, kind of. Otherwise, I'm like struggling a bit to explain everything right now. But yeah, okay. So if you know the transformer encoder, so what we do is basically we mask the attention. So we just don't allow some attentions to happen. And what attentions we don't allow is we don't allow training points to look at test points. Like their representations shouldn't be influenced by that, right? Because the test set shouldn't matter. And also tests, so that's like these arrows missing here. And also test points shouldn't rely on each other. It should be the same whether like my test set has like it's double the size maybe or half the size or something like this shouldn't matter. Yeah.
Maybe I'm misunderstanding, or maybe you already said it, but there seems to be a huge kind of downside compared to normal, obviously normal models.
Where you can look at everything, you mean?
No, when you use this, you need to run a transformer for every inference by using the training data set all the time.
Yeah.
Which means it was going to be.
It's slow at inference.
Slower by I don't know how many orders of magnitude.
Yeah, that is very, very true. We're working on that, and
five orders of magnitude, something like that.
probably more 10.
Yeah, like 10 orders of magnitude more expensive than inference.
In inference, yeah. So
That's a big deal.
Maybe that's not the point right now when we talk about the architecture.
No, just, I feel like, I'm understanding correctly, right?
Yeah. I think it's actually on the slide. I jumped over it. I don't want to oversell or anything. Sorry. So here, the high inference time, that's for sure a problem. And we also limited our analysis only to these like small tasks without categorical features. But we are working on this, and actually I think it's kind of solved.
May I ask how? Because it seems like it's fundamentally backed in here that you need to perform inference on the whole data set.
Yeah, so how you can get around this is you basically build your model in such a way that you can cut off these representations here somehow and save them for later. That's how we do it. I don't want to explain it exactly maybe right now, but you can like try to cut, like you can build, for example, a bottleneck. Your whole training data set representation has to go to a bottleneck, and you can just save the state of that bottleneck. And all of a sudden, your later inferences get really fast because you don't need to do this attention on the whole training thing.
Are you aware of this? There's a different formulation of large language models that also works quite well. It's called RKHV, where they don't have this attention thing. So there you could do probably very naturally by saving, processing the whole data set. And then you have an inference of order almost one, because you can use a hidden state. Like at rollout, it's an LSTM. At training, it's a transformer, but at inference, it's an LSTM. And then you could reduce the inference extremely drastically.
Exactly.
And they have very high performance.
Exactly. Something like this. Exactly.
Okay.
Very true. Yeah. That would be an architecture. Okay, so let's go going back to that definition, and what Tim also asked is where we don't allow attention from training to the test. We don't allow attention between test set items. So like it doesn't matter what other items are in the test set. My prediction will be the same. If I'm X4, I will get the same prediction out whether X5 exists or not. Shouldn't matter, right? So that we took care of that. And then we have attention on all the training sets. Everything can attend to each other as much as they want, right? Because they should build a representation of what the training data looks like by looking at what are the differences between the points and stuff like this. And how we make sure that we actually work on a set is super simple. Like transformers are kind of by like inherently working on sets. We just like for natural language force them not to work on sets anymore. And how we force them not to work on sets anymore is by having positional encodings. So positional encodings are vectors that tell your transformer, oh, I'm position 1, I'm position 2, I'm position 3. And we just throw them out, and all of a sudden the transformer is it's invariant to the order of the items in our training set. Yeah.
A short question: does your model, or is your model capable of generating multiple results for multiple data points from this X4 and X5 simultaneously, or do you have?
Yes.
Like okay.
Yeah.
And the second question is, which transformer like architecture did you base your transformer on? Because there are some transformers that have like this positional encodings in the attention itself. And then
we don't do that, of course. Yes.
Okay, yeah.
So I would say our architecture is like actually super close to the very original transformer architecture as proposed by Vaswani in 2017. Yeah. It's just the encoder of that, and we changed the attention masks. But besides that, it is this architecture.
And have you tried using a pre-trained transformer and like doing really transfer learning? Like it's obviously not the same topic. But
yeah,
using a pre-trained transformer
could be interesting. No, we never tried this because we thought like it's a different task. But I saw that people can use like pre-trained LLMs to learn like very different tasks, right? That's a thing that happens. So maybe it would help us as well. I don't know. Yeah. No, we never tried that. Okay. So maybe let's dive into how we generate the data sets really quick. So as we said before, like we have now this architecture that can accept the whole training set, right? Here D, and that can accept the X test. x4 and x5 and can make our predictions. So we have like the neural network that we need, but now we need the data to train it on, right? That's like the most important bit. Our prior is based on SCMs, but SCMs, I think, or how we think of them is basically a bit more fancy neural networks. And, or that's at least how we implement them. And what SCMs are, is structural causal models. That's what it stands for. And how people think about them or interpret them is each of these things is like an event in the world. And each edge here is like what causal relationship this event has with other events. So this epsilon1 here causes whatever, this node here, and epsilon2 has influence on these two nodes. And how we implement this is actually, we implement that very similar to a neural network, plus some noises, plus some like being creative on the activation function. So you can think of this, like each of these nodes holding one float value, and then this float value is propagated to these other nodes by being multiplied with some constant in this edge, getting and bias added to it, and then we apply a activation function like a ReLU or a tanh, something like this. And this way we propagate through the whole network. And what we then do is we randomly select what should be our x's and what should be our y's. And that's, I think, the very important distinction for the ones who know Bayesian neural networks, maybe, to Bayesian neural networks. And that is, our y is not always the top of this graph. Like y can actually cause some feature, or like they can have like some random relationship with each other. All we use this graph for is basically to build tables with columns that depend on each other in interesting ways. That's like the whole task here, basically. And so what we do, maybe we can go through this quickly. We initialize these edges, these constants. We decide what is x's and what is y, and then we feed random noise to this for every example in our training set. Like this is one particular D here right now that we talk about. And then we read the values off, and now we have our data set done. Oh, sorry, we actually discretize here, now done. Cool. And now we have a little bit on like how to use this. Actually, yeah, if you like, you can follow me here. So we, sorry. Sorry. We will jump to this other presentation here right now. And so if you like, you can run the tutorial yourself. It is linked on our GitHub page. That's AutoML/TabPFN. You can also read that QR code. I don't know if you have like a really good connection between your phone and your laptop. For some reason, you can scan QR codes to your laptop. But if not, you can type in this URL, AutoML/TabPFN, and you will get to this website here. And now here, there is the collab linked, and we can go through that collab. But this part of the tutorial is a little bit the boring part, I think, because it's only actually I have it open here. We only go through like a very sklearnish interface, but I can still show it really quick. Okay, I don't know. Do you guys need the link again, or you good?
Yes.
The link again? Cool. The link is github.com/AutoML, all smaller, lower caps, and then TabPFN. Yeah, Eddie?
How big are these models?
So this model here is very small compared to the models we talked about before, and it has 100 MB. So it's 25 million parameters.
Because it's up to 1,000, right? That's the reason.
No, actually, or maybe very indirectly, but generally it's like the same code that runs for every example in the data set. So you can actually feed it larger data sets. It would just be worse.
So you have weight sharing between the keys values.
Exactly. You I mean, in the transformer architecture, you only define your projections, right? And these projections always operate only on one time position. And
Yeah,
so
it's not the same weights.
no, it is the same weights on every time position.
Not the usual.
No, that's the usual. It's every time step shares weights. Okay, so when we run this now, we have like basically, so okay, why we have this right now is maybe to make you a little bit excited about the tutorial afterwards, because you see now that like if you train like a PFN, it can do something reasonable afterwards. And this is a PFN that we trained and that can do reasonable stuff already. And we will train our own stuff, but I mean, we will only do relatively short trainings. This training was like 8 GPUs for 1 day or something like this. We won't do this in this tutorial, but it's also not so far off. And what we have here, I'm sorry for all these warnings. What we have here is we have like that you can use this transformer with your standard sklearn interface. We like fit on the data and then you predict. And here we actually have this extra keyword that we want the probability of the winner out as well. And now you get your predictions out. And you can see, I don't know, here it has a good accuracy on this particular data set, but I mean, that doesn't mean too much. And what we can actually generate with this notebook as well is we can look at the decision boundaries. Maybe you know these plots from the sklearn website. What we have here is we have two features as x and y dimension, and we have a set of test points. These are the points with their true label, and we can see as like the background color which ones the TabPFN predicted as one class versus the other class, and we can see that interestingly it tends to make these kind of smooth curve, like smooth borders, something like. I think an SVM would make maybe similar borders to this. Sorry, it's like a kernelized SVM, I guess. GP might make similar borders. Yeah. Could you run this notebook? Or anyone struggling? Anything broken? No? Be honest. Okay, cool. So actually we can get to this like very fun part. How long do I have time? Until 5? 5:30. Oh, that's good. So we can get to the very fun part, or at least to me. I hope it's fun for you too. And we can jump over this recap here because we just had this recap. And we can now look at, so what we will do now is we will train this architecture that I talked about before in a little notebook. And we will now do regression though. The TabPFN can't do regression, but we will train regression. And how we will do regression is like what we found out works better than your typical prediction of like a single output is we predict or we discretize the output range. And now we predict the probability mass that falls into each of these discretized buckets. So we can say like our model predicts now between -3 and 3. And the area of each of these bars is basically what probability mass falls into each of these buckets. Does that make sense? So what this means is we can treat regression as a classification problem. Okay, so if like something falls in here, The correct thing is just to predict, oh, it's somewhere in this bucket. Okay.
Isn't this?
Yeah.
I'm not sure whether I want to ask that, but isn't it a little bit weird? And wouldn't you usually do it the other way around? I mean, maybe I.
No, yeah, no. I think that's a very good point. I think it's weird too, to be honest.
Because I mean, all your motivation in the beginning, like when you did the Bayesian setup, it was all regression, right?
Yeah. But this is the only way we can do something, we can predict more interesting distributions, right? Because when you have these bars, you can, for example, have a bimodal distribution that comes out. Or you can have, I don't know, something that falls off on one side and goes like very straight on the other side.
Disregard my question.
I mean, or what I compare to is basically the standard thing where you predict the mean and the variance, like that. Like that's the competition we tried out. Probably there are more fancy things you can do as well that might be non-discretized. But I kind of like, my theory here is a little bit that transformers were built for classification, so probably they're just good at that because we built them for that. Yes.
Maybe it's also helpful that you don't have like a parametric assumption on how the this output distribution is. So this is like non-parametric. In the other case, you basically have to know like what's my Gaussian like noise that's on like the Y. So that might also be helpful.
Yeah, that's my reasoning too. Sorry, yeah. Okay, sorry. And like the notebook, I don't know, I want to make you hot for this tutorial. This notebook is, I think, very relevant. I actually used this notebook very recently, like did some toy experiments in the notebook and tweeted it, and it went kind of viral. So this notebook is kind of the cool, right? It's cool, little bit viral, like my standards viral. So okay, let's get our hands dirty, and let's start with this notebook. And I will kind of tell you as we go a little bit what's going on in the notebook, but I added a lot of comments as well, so probably you don't really need me, I hope. And we did that already before this notebook, so I reworked most parts and should for sure run. There, you can actually run it locally if you really want to and hate Colab, or maybe you say you don't use Google or something like this. Then you can use, we have the copy of our notebook on our GitHub. And if you don't say you hate Google or something like this, and you just want to be practical and don't want to like trash your computer with my code, then you can run it on Colab, which is what I would recommend, because like last time at least, most people struggled, like, I don't know, something doesn't install or something in their local setup. So I think it is easier to run it in the Colab. For either of these cases, you can actually use this domain as well. So you can go to AutoML/PFN uppercase, lowercase s, and then there's a link to the Colab as well there. So I don't know, I showed a lot of links to AutoML, so to the AutoML GitHub now. You probably know this, and then you go to PFNs there, click on the link for a Colab. I can maybe do it here so that you see it. So this is the page, and now here's the tutorial, and then here is the starting with the Colab. I think the tutorial links also the Colab. Doesn't matter where you click. Someone who can't find the link right now, maybe should I show the link again? AutoML/PFNs. I think this is the, or I mean, if you're really good with typing, you can do the other. So what we will do now is we will train PFNs to do linear regression for us. And then we will train PFNs to do more funny linear regressions for us, where we have signs in the lines, where we want to predict the mean of the sign, stuff like that. And you should all use the GPU. I really recommend that. I think it's like 4 times faster or something like this, or maybe 8 times faster. So if you're on Colab, you can click up here, edit, and then you click. No, is it really edit? Notebook settings? Edit notebook settings, and now you can select the GPU here. I recommend the GPU. I never tried it with the TPU, so I can't say anything about that. And after you installed the PFNs, you might actually get an import error. And in that case, you need to restart the notebook and it will work. And you restart the notebook by clicking runtime and then restart runtime. If you're on GPU, it should say T4 here in the upper right corner. I can make it larger again here. It should say T4 in the upper right corner. Okay, if you get this import error, restart the notebook by clicking runtime, reset runtime. And then this import should work. If it still doesn't work, I come over. Okay, maybe I just like one sentence regarding this like first prior, maybe it's not super clear to you, but rich regression can be viewed as a Bayesian model as well, where our uncertainty is like basically over where the line goes through, and this rich, like this regularization part basically adds the uncertainty. And when we want to get PFN to do something like rich regression, all we need to do is the following, and there I linked a blog post, I think, further down. I didn't link the blog post, I'm sorry for that. Okay, you have to Google for it if you're interested, I'm sorry. Yeah, what all we need to do, and in that blog post they elaborate on it a lot, is basically we need to define our output without noise. Here I call it f as x, the dot product between x and some vector w, and we will come to that vector later. And then we add some normal noise around our values with some noise a here, and our vector w we need to sample also from like a very simple normal distribution around 0. And like that's all we need to do. So we sample first. In reality, we do everything the other way around, right? We sample first w, then we generate our f, and then we sample y around f. And that's what's going on here. We sample our w here, like a normal distribution around 0. Then we sample some inputs x's. So I left that away before. So we need some points on the x-axis, but that doesn't really matter for us too much. And what we then do is we do this dot product. I do this here with an einsum. And what we then do is we again have a normal distribution with standard deviation A around these points.
Maybe just, if I'm allowed to say this, I mean, if there's a single person in the room who has not seen this before, this does not hold only for rich regression, right? That holds for any model with a rich penalty.
Okay, you know more than me on this, I think. Okay, yeah, if you, I don't know actually. Okay, cool. With the rich penalty, that's like a minus the L2 norm or plus weight. Plus the L2 norm weight, yeah. Cool. So if we do the above, we get these lines, and I guess this is not really what you expect. They all start in the 0, 0 in the 0, 0 coordinate. So we just introduce another axis, which is like the bias axis, and all we need to do there is we just sample one more point in our w. And so here you see our new w doesn't only have num features, but it has one extra point, and that extra point is kind of getting fed a feature that's always 1. So if we think about the dot product, this will be multiplied by 1. So what we get here is like a random bias that is sampled from the same normal distribution. And now we get curves that look much more like what we expect. I don't know, the curve is the wrong word, I guess. Lines that look much more like random lines that are like arbitrary in space, how we expect it. And for our code, we need a particular format for these samplers, and this comes in the next step. So we always have these get batch functions, and these get batch functions, they take in how many curves to sample, how many points there are on the curve. So this is, for example, 100 points. So what that means is we want 100 x's, like a data set of size 100, that means basically. And we want to say how many features we want. And this is all we need to define. And then down here we have a training loop. We don't have to look into the training loop right now, but we can now train a PFN for this particular prior. And our prior is really defined as this getBatch function, because what this getBatch function does is it samples random data sets from this prior. So it's the whole definition we need for the prior. And in this notebook, you will now go through different priors and different getBatch functions, and also get creative on yourself, like what getBatch functions you want to build. And because as you see, like these getBatch functions is like 10 lines of code or something like this. They are rather simple. Does it help if I go through this particular one maybe again, like line by line, or is it kind of clear for everyone what's going on? I don't know. Yeah, depends, I guess, on how much Torch code you've read before and stuff like that.
If we have the time, just do that line by line.
Okay, cool. So if you, yeah, don't listen to me if you know it, but if it helps you, listen to me. I guess that's like the normal standard, the default for a talk. Whatever. Okay. So we have this getBatch function, and the important thing for our code, for our training loop, is that we follow this this format where we have these arguments up here. We can actually have some more also, and we return an object like a batch object. And the batch object consists of an x, a y, and a target y. For now, let's treat y and target y as the same thing. It's basically both y. It's just, yeah, ignore the target y. You just like copy y there. It's okay. And how we sample our w, so this is like the curvature of our lines, is we take a normal that is centered around 0 with the number of features plus 1, and this one extra feature is for the bias. So how high should it start? Like what should be the height at x equals 0 of our y? So what should be our y at x equals 0? And we sample this with our standard deviation b. That's the b we defined up top in the first equation. And we sample this batch size many times. So we want batch size many w's, because in every data set should be ideally uncorrelated in this particular batch. We don't want like 5 times the same line, or we want different lines. So we sample batch size many, and now we define our inputs, and our inputs are chosen in the unit cube, but like completely at random, like random uniform, inside the unit cube. And you can see here we have batch size many x's, and or batch size many data sets, second many examples in each data set, and num features. And now we project these. So this is the heart of the thing, I guess you could say. And this projection goes in a few steps. So first we concatenate with our axis a 1, because we know this multiplication of 1 with something else is always this something else, right? It's identity operation, and we just want to add this this bias to our terms. And what do we multiply in this dot product? So what we have here is a dot product. We do the x's with the w's, and we can read this term up here is we have 1 w for each data set. That's why the m is missing here. The m is the number of examples in each data set, and the n is the batch size. So I can actually also rename this batch size, and then maybe call this s, because we call it segment all the other time. Batch size, segment, and then we have f is the number of features. So batch size, segment, and number of features. Oh, and what we want to get out is we don't want to get out many y's, right? There's only 1 y per example. That's why our output is only batch size, segment, sequence length. And now we sample some noise around this, and that's our y. And now they like a little bit of a weird thing. I'm sorry for this. Our code always has like as a convention batch size as the like dimension number 1, like or second dimension. Like batch size doesn't come first for us, it comes second all the time. It's like traditional transformer code. By now people actually code it differently. We just stuck to it. Sorry for that. But just so you know, like you will see these transposes always in the end. It's just because our code expects batch size in the starting from 0 first dimension. Okay. Okay, maybe I come around, or did you do it in the other tutorials? I can come around. Oh, yeah. Yeah, so maybe if you have questions, raise your hand. I think I won't explain like all of the parts because I think the text should explain it. Maybe if you don't know torch so much.
So I'm pretty sure you already explained it, but I didn't have got this answer.
Yeah, so Einstein is basically like a combination of summing and multiplying. And yeah, if you don't know what it's needed, it's hard to remember, no, but you think of it basically as like a bench of that's all that does. I can also rewrite it without that, so maybe that helps.
It's actually really faster or better.
For me, it's easier because I'm used to it, but I maybe shouldn't have used it.
I think
in
it's just
such a public
preference.
place.
Yeah, equivalent operations to do it without it.
I think he did not.
I don't have something, yeah. Right.
Actually, I don't know the other, like, I don't know another way to write this now, but probably ChatGPT knows, I guess. Okay, this is batch matrix multiplication. So I guess that's the way. Okay, maybe this helps you. What? Yeah, sure. Maybe really quickly for everyone, I defined like a train PFN function here, but this is like just a very light wrapper around our standard train function, and the idea is only to like put in some defaults that make sense. You don't really need to read this part of the code, but if you're interested in transformers, you can, for example, change the architecture in this line. Stuff like this is kind of open and closed, I hope. But you can treat this thing as like it kind of works.